Hello everyone, my name is Harindu Jayaratna. I will be presenting our work DualCam, a novel benchmark dataset for fine-grained real-time traffic light detection. This research was carried out by University of Monatua with my colleagues Tarindu Samarakon, Hasara Koralege, and Asita Divisekara under the supervision of Dr. Ranga Rodrigo and Dr. Peshala Jayasekara. Traffic light and sign detection is an important perception task in advanced driver assistance systems and autonomous driving systems. In this research, we focus on traffic light detection and observe that real-time traffic light detection has unique challenges compared to traffic sign detection. For example, traffic lights have smaller object sizes, variation in illumination, close resemblance with other objects introduce false detections, dynamic nature of traffic lights, and computational resource limitations. We observed that using a multi-camera approach would improve the accuracy of existing traffic light detection methods. Large amount of both public and private traffic light datasets are available in the literature. However, existing datasets still could not be used to develop algorithms in our multi-camera approach. In this research, we provide a traffic light dataset covering 10 object classes captured using a narrow angle and a wide angle pair of cameras. Synchronized test videos for testing purposes are also provided. We propose a simple, pragmatic post-processing algorithm to combine the output from the two cameras in a resource-constrained detection environment. We provide evaluation results of our benchmark dataset in terms of speed and accuracy, using a state-of-the-art object detection model as a performance baseline. Our data collection and annotation process. Initially, we collected street footage in urban and semi-urban areas using two vision grid busler dart cameras with different field of view angles. Horizontal field of view of the cameras are 48 degrees and 125 degrees. We mount both cameras close to each other behind the windshield of the vehicle. Frames containing traffic lights are then extracted and manually annotated using CVAT annotation tool. The annotations are provided in both Pascal VOC XML format and YOLO format. Our dataset consists of 2,658 images in total. Out of them, we make sure 813 image pairs are synchronized image pairs to facilitate testing the accuracy of dual camera detection. Our dataset contains 8,321 traffic light instances in total, covering 10 different classes. Table 1 shows the number of instances available in each class. There is an inherent class imbalance between the classes of the dataset. Moving on to the detection pipeline used for traffic light detection, output images of the narrow angle and wide angle cameras are fed to the object detector for detecting traffic lights as an input of batch size 2. Object detector will output the detected traffic lights as bounding boxes. We finally use a post-processing algorithm to combine the outputs from the both cameras onto the wide-angle camera frame. The post-processing algorithm involves the camera parameters to map the bounding boxes into the wide-angle output using homography. One inherent problem in such mapping is the double detection of same object in the middle of the image frame. The algorithm further removes the double detections and obtains the output as if the detection was performed using a single camera. The method proved to be a pragmatic and resource-efficient approach to obtain fine-grained traffic light detection. As the object detector, we used YOLO V5 detector. Moving on to quantitative results. Table 2 shows the F1 scores obtained for each class under two YOLO V5 models. It is evident that YOLO V5L performs better compared to YOLO V5S in accuracy, but it is a trade-off for inference speed. The table highlights the tendency of the object detector to perform better in certain classes compared to others. Figure 5 shows the class-wise precision recall curves for the two models. It shows the tendency of the traffic light detection to have low recall values as mentioned in the literature. In traffic light detection, even though precision can be improved to higher levels, recall has limited improvement capacity. The ground truth used to evaluate the performance includes bounding box size reaching a minimum of 6 pixels. We employ NVIDIA Jetson AGX Xavier device as a resource-constrained environment. Furthermore, we compare the performance with the RTX 2080 Ti GPU. Table 3 compares the detection speeds of the normal approach with the multi-camera approach. Figure 6 and Figure 7 shows the trade-off between inference speed and accuracy due to dual-camera approach. Batch 2 plus post-processing has resulted in little increase in delay compared to the normal approach. Figure 7 shows the increase in detection accuracy because of the dual-camera approach. The ground truth used to evaluate the performance in Figure 7 includes bounding box sizes reaching a minimum of 1 pixel in the wide-angle camera frame. In summary, our work introduces dual-camera traffic light dataset covering 10 different traffic light classes, addressing the need of datasets for developing multi-camera traffic light detection algorithms. We have evaluated the effectiveness of the dual-camera detection approach and the single-camera detection approach for traffic light detection task. The dataset is provided with two annotation formats to facilitate subsequent research in traffic light detection. Our dataset is publicly available at the provided GitHub link. Thank you very much. Hope you enjoyed our presentation.